For recording. Okay.
Yes, you can start.
Okay, thank you. I will chair today's seminar. I think that's the fourth seminar on inverse problems theory and applications. We have a talk titled "The Inverse Problem for Differential Operators on a Star-Shaped Graph with a Non-Local Matching Condition." This topic will be presented by Professor Natalia Bondarenko from Samara National Research University, Saratov State University. So, Professor Bondarenko, please, you may present your work.
Thank you for the introduction. I'm grateful to all the organizers for the opportunity to give this talk. Here is the contents of my talk. First, I'll tell you the problem statement. Second, I'll tell some words about historical background of the problem. Then I'll tell the main results. And finally, we will discuss the relation of this problem to functional differential operators with frozen argument. This talk is based on this preprint of year 2022. And further, I will refer to this preprint as a star. So if I mention a star, it means this preprint. So if I don't have time to tell some details, you can look in the paper. So let's start from the problem statement. Consider the following eigenvalue problem L on the star-shaped graph. This problem corresponds to such graph having m edges, and every edge can be considered as the interval from 0 to pi, and for convenience, we assume that 0 corresponds to the boundary vertex and pi corresponds to the internal vertex. And on each edge, on each segment, we have the Laplace equation. Here x is from 0 to pi, and g is from 1 to m. So we have m such equations. Two other boundary conditions at the boundary vertices. And we also have the matching conditions 3 and 4. 3 are the continuity conditions. So we have a function yg at each edge, and at the central vertex, the values coincide. And we have the matching condition 4. This is a non-local condition with an integral term. Here, lambda is the spectral parameter. H, G are complex numbers. PG are complex valued functions from L2. And we will consider, this is the same problem, we will consider inverse problem 1. Given the spectrum lambda of the problem L, find the functions PG of this non-local condition. The numbers HG are supposed to be known a priori. Further, we will have some additional restrictions on these numbers. But first, I'll tell some words about historical background. Differential operators on graphs arise in various applications, in particular in organic chemistry, mesoscopic physics, nanotechnology, and many others. There is an extensive literature on differential operators on graphs. Here, I provide only a reference to this book by Berkolaiko and co-authors about quantum graphs and their applications, and the reference to the survey by Yurko, who is one of the best specialists on inverse problems for differential operators on graphs. And this is an overview of inverse spectral problems for such operators. The most important results in this direction are concerned with the recovery of the differential expression coefficients, for example, of the Sturm-Liouville potentials from the differential, from the second order differential expressions on the graph H. Also, I should mention that the majority of studies of differential operators on graphs deal with local matching conditions. In particular, the so-called standard matching conditions are often considered. These are the conditions of form 3-4 with PG equals 0. So if here we have just the sum of the first derivatives, and we have these conditions. Such conditions are called the standard matching conditions, and they are natural for various applications. However, for modeling some physical processes, non-local conditions appear to be more adequate than local ones. What is known about those problems for operators with non-local conditions? Such problems with non-local integral boundary conditions on finite intervals were studied in the series of papers by Kravchenko and by Young and Yurko. But in these papers, the coefficients of integral boundary conditions are assumed to be known a priori, and the problem consists in the recovery of differential expression coefficients. These problems considered in these studies, they are different from the problem considered in this talk, because here in this talk we will recover the matching condition coefficient, but here the differential expression coefficients were reconstructed. The idea of this study, of my study, has been inspired by the paper of Kangusian and co-authors, which is concerned with recovering coefficients of non-local matching conditions of differential operators on a star-shaped graph from spectra. But in this paper 7, this paper 7 has some principal disadvantages. First of them is that in 7, another type of non-local matching conditions was considered. Those matching conditions do not generalize the local standard matching conditions, which are regular and natural for physical applications. So in 7, there is completely another type of non-local matching conditions. Also, the method of 7 requires the basicity of eigenfunctions, but it's unclear whether this basicity holds in any cases. In particular, one can easily find an example of non-basicity. And also, the authors of 7 confine themselves to the so-called identification problem that consists in the reconstruction of the unknown coefficients. The existence of inverse problem solution has not been investigated. In this study, in the preprint STAR, we not only provide a correct problem statement and develop 2 constructive methods for its solution, but also obtain the spectrum characterization for the problem L. So we also study the existence issue. Now proceed to the main results. Here is the problem statement. Again, recall that HG are the boundary conditions coefficients. Denote by ZK the roots of this polynomial. You see here, this polynomial has the degree m-1. So here are m-1 numbers. We will use this notation if Hg are complex numbers and all the values Hg and Zk are distinct. In particular, H belongs to this set in the special case when Hg are real and distinct. Indeed, if Hg are all real and distinct, it can be shown that the roots of this polynomial are also real and distinct, and they are distinct from Hg. And the main result actually is the following theorem, theorem 1. Suppose that H belongs to this set. For a multi-set lambda to be the spectrum of the problem L of form 1,4, it's necessary and sufficient to be countable and to have such numbering by two indices, n from 0 and k from 1 to m, such that the following asymptotic relations hold, where the remainder terms are from L2, that one is this number, and that k, for k greater or equal than 2, are these numbers defined above, the roots of this polynomial. So we have one subsequence of this form, and for k from 2 to m, we have such subsequences. Also pay attention that here is kappa n1 divided by n, and here is kappa nk divided by n squared. This is a non-trivial thing, and it's important for the reconstruction. If we don't have this n squared, we cannot recover the functions PG. So this is important. Moreover, the functions PG of the problem L are uniquely specified by its spectrum lambda. So this theorem gives the spectrum characterization and the uniqueness of inverse problem solution under this condition. Also note that the sequence lambda and k can have a finite number of multiple eigenvalues. For large indices n, the eigenvalues are simple because of the asymptotics 5. Since here that k are distinct, we have that for large n, all the numbers lambda and k are distinct. Also, we observe that the numbering of lambda and k in theorem 1 is not uniquely fixed. The numbering of some first values may be arbitrary, and all the arguments below are valid for any such numbering. Now proceed to the proofs. Define the functions phi g. Clearly, for each fixed g, the function phi g satisfies the corresponding equation 1 and the boundary condition 2. So phi g satisfies the equation, the Laplace equation, and the corresponding condition. It can be easily shown that the eigenvalues of the problem L coincide with the zeros of the characteristic function, given by this formula. Obviously, this function is entire analytic in lambda plane, and the necessity of the asymptotics 5 can be proved by the standard approach based on Rouché's theorem. So now I'll not tell about this, and we mostly focus on the proof of sufficiency. We prove the sufficiency by two different methods. Let's start from the first method. First, we need this lemma. The function phi g at pi lambda has only simple zeros if and only if this condition holds, hg doesn't belong to some set. And further, for simplicity, we will assume that this condition holds. So phi g at pi lambda has only simple zeros. In particular, this is so if hg is real. Suppose that this condition holds, and lambda and k are arbitrary complex numbers satisfying the asymptotics 5 of theorem 1. Construct the sequence of vector functions y and k according to the following definition. And here is the definition. it's a little bit technically complicated. For any value lambda diamond from this sequence, we define the chain of vector functions with diamond. Here the number m diamond is the multiplicity of this value. So this is the number of occurrences of this value lambda diamond in this sequence. And y diamond with 0, y diamond with 1, etc. They are defined by different formulas in different cases. The most important that they are vector functions of size m, and they are defined by phi g. So if we know phi g and we know lambda and k, we can define this function, vector functions, and then we put them into one sequence and obtain the sequence y and k indexed by the same indices as lambda and k. So if we have a multiple value lambda, we can obtain the same number of vector functions and then put them all together into one sequence. So we get some sequence of vector functions, and then we prove the following lemma. If lambda diamond is an eigenvalue of the problem L of algebraic multiplicity m diamond, then the corresponding vector functions constructed by this definition is the corresponding chain of root functions of this problem. That is, root functions are the eigen and associated functions. This means the following. This is the standard definition of the root functions. So if lambda diamond is an eigenvalue, then they are the root functions. However, if we construct y and k by an arbitrary sequence lambda and k with asymptotics 5, we do not know whether they are root functions of some problem L or not. In fact, we will prove this, that they are the root functions of some problem. Then define the Hilbert space of vector functions H. They are the vector functions of size m with entries from A2 with the standard scalar product. If y and k are the root functions of L, then the condition 4, this is the non-local matching condition, implies this important relation 9. Here we have the scalar product in this sense of y and k and of this vector function p, which consists of components pg with a complex conjugate. And this scalar product equals to the sum that can be calculated by if we know y and k. Further, we define such functions. V and k are actually y and k multiplied by some constants. And the following lemma is proved. The sequence v and k is a Rees basis in H. If the vector functions v and k are constructed by using the eigenvalues lambda and k of a certain eigenvalue problem L, then using 9, this formula and the definition of v and k, we easily obtain this relation 11, where eta and k are have this form. So this relation is known if they are constructed by the eigenvalues of a certain problem. If we want to prove theorem 1 by sufficiency, we use this relation 11 to recover P and to prove theorem 1. So we arrive at the following algorithm 1 for solving the inverse problem. Suppose that H is from this set, and complex numbers lambda and k satisfying asymptotics 5 are given. We have to find PG. First, construct the vector functions y and k by definition 1. Second, find v and k by multiplying y and k by some constants. Third, construct the B orthonormal basis b and k with star. That is such basis that this holds. Then find the numbers eta and k by these formulas. And then find the vector function p satisfying 11 by this formula. If this is just the reconstruction of p by its Fourier coefficients. And the elements of these vector functions are the desired functions PG. Note that using this method, we not only solve inverse problem, but simultaneously prove the risk basis property of the root functions. In fact, the basicity of root functions for operators with non-local integral boundary conditions has been studied before, and this theory is rather well developed. In particular, the basicity of root functions was studied by Shkalikov for the higher order differential operators with integral boundary conditions, and by Gamilka and Radzievsky for the vectorial functional differential system of this form. Here y is the vector function, and here if y is actually also some non-local term, it can be, for example, integral differential and with integral boundary conditions. So this is a rather general object. And of course, there were many other papers in this direction. However, when we study the inverse problem, we do not know that y and k are the root functions. So we cannot directly apply the known results on the basis property of the root functions to this sequence. Now, let me proceed to the second method. And I think, in my opinion, this method is even easier than the first one. Recall that the characteristic function has this form. Define the function delta 0 of the same form, but with PG equals 0. And delta hat of lambda is the difference of these two functions. It has this form, 13. For each g from 1 to m, we consider the zeros mu and g of the function phi g at pi lambda. Under our restrictions, phi s, so these zeros of phi g are not the zeros of phi s if s is different from g. So the zeros of these functions are different. Substituting lambda equals mu and g into 13, we derive this formula where he and g can be calculated by this formula. So here we have m terms, but if we substitute mu and g, all of them are zeros, and only one is non-zero. The one which doesn't contain, the one which corresponds to this g is non-zero. And these numbers are non-zero, as we have already mentioned. And using this relation, if we have this relation, it means that we know the Fourier coefficients of PG with respect to phi g of x, mu, and g. Observe that mu and g and phi g at these points are the eigenvalues and the eigenfunctions, respectively, of this boundary value problem. Indeed, phi g satisfies this and this relations, and we add such boundary condition. Therefore, since they are the eigenfunctions, the sequence is a Riesz basis in L2. And so we can use relation 14 to solve the inverse problem. And we get the following algorithm. Suppose that H is of this class, and complex numbers lambda and k satisfying asymptotics 5 are given. We have to find PG. First, construct delta of lambda by as an infinite product by its zeros. So this is the formula which can be obtained by the standard methods of construction the entire function by its zeros. Second, find delta 0 and delta hat by the formulas. Then, for g from 1 to m, implement the following steps from 4 to 7. Find the zeros mu and g of phi g at pi lambda. 5. Find the sequence W and G be orthonormal to phi G. Then 6, find he and G by the formula, which was already presented, and then find PG satisfying 14. 14 is this relation. So if we know, if we want to recover the function PG from its Fourier coefficients, we use this formula. So by using algorithm 2, we obtain an alternative proof of the sufficiency and the uniqueness in theorem 1. In this proof, the asymptotic formulas for delta hat of lambda and for he and g are important. So actually there are some technical calculations of asymptotics are required, and this algorithm also allows us to prove theorem 1. Now let's consider such question. What happens if AG are not all distinct? The paper star also contains answer to this question. Note that the condition HG is different from HS is crucial for the uniqueness of the inverse problem solution. Suppose that, on the contrary, HG equals HS for some different indices G and S. Then every term of the characteristic function contains the multiplier phi s, because here we have the products of all the phi s excluding one value. And if two of them are equal to each other, then we have this phi s in each term of summation. And therefore, the spectrum lambda, the zeros of delta, contains the subsequence mu and s of the zeros of this phi s at pi lambda. And this this subsequence carries no information on the functions PG, because it doesn't depend on PG. It depends only on phi s. So this is the main idea. What happens in this situation? Then there are rigorous formulations. Maybe let us not elaborate into the technical details. The main idea is the following. So suppose that there are equal values among HG and they are consecutive. And we introduce their multiplicities, and finally we obtain the characterization theorem for this case. For a multiset lambda to be the spectrum of this problem, it's necessary and sufficient to have this form. So the spectrum consists of two parts. The first part consists of mu and g of the zeros of phi g at pi lambda, And the second part are some other numbers, lambda and k, which satisfy such asymptotic formulas where that k are different from the ones in the previous theorem, that k are the zeros of such a polynomial, of some other polynomial than before. Moreover, the spectrum lambda uniquely specifies the sums of PG. You see, I said that in this case, there is no uniqueness of inverse problem solution, but we can uniquely recover some sums of functions, PG. Obviously, this part of the spectrum carries no information on the functions PG, and these sums can be recovered from the part lambda and k of the spectrum lambda by using algorithm 2 with necessary modifications. Actually, the proof is similar to the proof of the first theorem by the same algorithm with necessary modifications. So these were the main results. And now it's important to mention that there is the close relation between this problem and the problems with frozen argument. Because the adjoint problem to the problem A given by 1,4 has this form. This is also the problem on the star-shaped graph, but it has the frozen argument pi at the central vertex. So here we have the equations with frozen argument. The boundary conditions are of the same form. This is the complex conjugate. And the matching conditions are the standard. So they don't contain the non-local term. These two problems are adjoint to each other. So the spectra of L and L star are complex conjugate to each other. Thus, inverse problem 1 is equivalent to the following inverse problem 2. Given the spectrum of the problem L star with frozen argument, find the functions PG. So it's easy to see that actually this is the same problem. So theorems 1 and 2 provide the spectrum characterization and the uniqueness of solution for inverse problem 2. In fact, the inverse problem theory for functional differential Sturm-Liouville equation on a finite interval with frozen argument has been intensively studied in recent years. The majority of studies in this direction belongs to Sergei Buterin and his co-authors. So here, Buterin and Vasiliev, Kuznetsova. Also, there was the paper by Chinese mathematicians. This paper with Tsai, it also contains Buterin as a co-author. This is the continuation of this list. Some important results recently were obtained by Kuznetsova. She obtained necessary and sufficient conditions for the spectra of such operators. Using the methods of this talk, the methods of preprint star, one can obtain the results of the mentioned papers concerning the inverse problems for the functional differential operators with frozen argument on a finite interval in another way. So our methods can be also applied to these problems. Let me describe the main idea. Consider the boundary value problem 2021. So here we have the Sturm-Liouville equation with the frozen argument on a finite interval. And here alpha and beta can be 0 or 1. So these conditions can be Dirichlet and can be Neumann. The adjoint problem has the following form. You see, we get the Laplace equation, we get the same boundary conditions, and we have such discontinuity condition of non-local form. And this problem can be rewritten. The latter problem is equivalent to the following boundary value problem on the 2H graph with integral matching condition. So we can represent this interval as a graph consisting of 2H, and on each H we get the Laplace equation. We get the boundary conditions, and we get the continuity condition, and this condition with integral terms turns into such condition of the same form that was considered in the stalk. The difference from the problem in the stalk is that here L1 and L2 may be distinct. The length of the H may be distinct, but actually this is not very important. The method works for this case. And the inverse problem with frozen argument now can be reformulated as follows. Given the spectrum lambda n of this problem, find P1 and P2. Because you see these functions, if we find these functions, we will find the potential Q in the initial equation. Denote by phi g the solution of equation of the Laplace equation, satisfying the corresponding initial conditions. They are either sines or cosines. The eigenvalues of the problem coincide with the zeros of the characteristic function. And we obtain the following two cases. There is the degenerate case if phi1 and phi2 at L1 and L2 respectively have common zeros. Then the zeros are also the zeros of delta of lambda, so we get some eigenvalues which carry no information on P1 and P2, and therefore the solution of inverse problem 3 is non-unique. And there is the non-degenerate case when phi1 and phi2 do not have common zeros, and then the solution of inverse problem 3 is unique. These cases are the same as in these papers. In the non-degenerate case, the solution of inverse problem 3 can be found by a constructive procedure similar to algorithm 2. The difference is that here we have different L1 and L2, but this is not important. Following the strategy of method 2, one can obtain the spectrum characterization for this case. The methods of this talk can be used for the development of inverse problem theory for the operators with frozen argument on a finite interval. For example, the following operator can be considered, which, as far as I know, it was not studied before, where we have two potentials. One at y of x is known a priori, and this q of x is unknown and has to be recovered. Then we can do the same thing. We can obtain the adjoint problem. Then this P will be in the equation, and Q will be in the integral condition. And then if we know P, then we can recover Q. So this method also can be applied. Now I'd like to say some words about inverse problems with frozen argument on graphs. Because for such problems, there are only some fragmentary results. In particular, Sergei Buterin in the conference proceedings. Unfortunately, they are only in Russian language. Sergei has announced some results on inverse problems for operators with frozen argument on graphs. I hope that this paper will be published as a complete paper in English language soon. There are also some studies concerning non-local self-adjoint operators having both frozen argument and integral boundary conditions. So the self-adjoint, in the self-adjoint situation. Such problems were studied by Nizhnik and by some of his followers. In particular, in the paper 24, Nizhnik considered such operators on graphs. But those operators on graphs cannot be uniquely recovered from the spectrum. So there is no uniqueness, unfortunately, for such problem. And also I'd like to mention this important paper, which appeared recently by Dobasevich and Khrynev. Dobasevich and Khrynev have obtained the spectrum characterization for the rank 1 perturbation of the form 25 of an abstract self-adjoint operator A in a Hilbert space H. The spectrum of the operator A is required to be discrete, simple, and separated. Separated means this condition. So they considered an abstract situation, but there are some very restrictive conditions on the operator A. In particular, this form corresponds to the Sturm-Liouville operator with frozen argument if A is the Laplace operator with an appropriate domain, phi is the Dirac delta function, this phi is the Dirac delta function, and psi is q of x. If we substitute these values, we get the operator, the Sturm-Liouville operator with the frozen argument at the point A. The method of Dobasevich and Khrynev can also be applied to operators on graphs. So we can take A being the Laplace operator on graph. In particular, their results, these results imply the results of this talk, in particular theorem 1, in the self-adjoint case, when all AG are real. But if they are complex valued, then the operator A becomes non-self-adjoint, and in the non-self-adjoint case, the method of 25 doesn't work. But the methods of this talk, as well as the methods of Buterin and others, work with minor modifications. Actually, the methods of this work are not very different for self-adjoint and non-self-adjoint case, but this theory is constructed only for the self-adjoint case and with these restrictive conditions. So I believe that the methods of this talk and of the mentioned others studied the operators with frozen argument, they will be more effective for the future research. So this is all. Thank you for your attention.
Professor Bondarenko, thank you very much for your presentation. It's time for questions and comments. Are there any questions?
Okay, I have one question.
Okay.
In the case, the frozen argument on the finite interval, how many spectra is enough to determine? No, not this. we have
graph
operator with q of x and plus q of x.
You mean this operator?
This one.
How many spectra is enough to determine the q of x?
You see, if we know p of
Yes.
x a priori, if we know this function a priori, and we want to recover q, then I guess then one spectrum is sufficient. Actually, I haven't studied this problem in detail, but it will be one spectrum. One spectrum will be sufficient if it's non-degenerate case.
Okay. Actually, it is solved or it is not solved yet?
No, it's not solved yet,
Okay.
but I believe it can be investigated by this method.
Okay, thank you.
I also have a question,
Mm-hmm.
Professor Bondarenko. I would like to ask about the numerical aspect of this spectral problems, inverse spectral problems. In fact, I don't know much about the such problems, but I saw one of your paper, I think, in one page, finite difference on this problems.
This one, yeah.
Yeah, 18, I think. Just a bit. Can you mention a couple of things? Thank you.
What is your question?
For example, in spectral problems, what happens if we have a variable coefficients, for example, as the coefficient of y double prime, second derivative, or okay, let me ask in this way. In paper 18, I think that's your paper, right?
Yes, it's my paper.
Yeah. I wonder, I mean, what is the difference between 18 and the one you mentioned here? Are they the same?
The difference is that in this paper, the problem is the problem on a finite interval is studied, not on the graph, but on the finite interval. And actually, this problem, it concerns the numerical methods.
Yes, that's what I'm asking, in fact.
Yes, in this problem, you see that the majority of the papers, they concern the continuous case, the differential equation. But this equation can be approximated by the difference equation. And then we get the discrete problem. And in this problem, first, the discrete problem is studied. So the inverse problem theory is constructed for the discrete problem, but actually it's not very difficult. It's rather easy because it's just a linear algebra.
I
but
see.
Then the numerical method is developed, which is based on the reduction of the continuous problem to the discrete problem. So if we have a finite number of the eigenvalues of the continuous problem, then we can approximate the eigenvalues of some discrete problem, then solve the discrete problem, and then to obtain the approximation for the solution of the continuous problem. So this method is developed.
I see. Thank you very much.
You are welcome.
Any questions? If you have any additional questions, once again, thank you very much, Professor Bondarenko. And we can finish today's seminar, and we will see in 15 days. Have a nice day.
Thank you.
Have a nice day.
Thank you.